Okay, so my name is David Saccon from Ericsson, and I'm here to talk about Unified MPLS. So basically, where this is coming from is this is a transport architecture using MPLS. Obviously, you know, as Ericsson, we look a lot at mobile networks, and we think a lot about kind of how you know, in various stages these networks are starting to leverage the assets and infrastructure for both fixed and mobile. So if, you know, in certain parts of the network, we see, you know, this infrastructure coming together. For instance, if you look at the edge of the network where services are delivered, then we can start to see solutions and kind of elements of consolidation and convergence where certain platforms are leveraged across different functions, different services. We have kind of solutions which are end-to-end proposals in terms of how to, you know, have handsets which are, you know, mobile handsets which typically get authenticated in the mobile network using SIM-based authentication technologies. There are Wi-Fi solutions which allow users to get access to bandwidth in their home or in certain Wi-Fi sort of hotspots, which is using this authentication from the mobile network. It uses the packet core assets that the mobile network uses, but it's leveraging the fixed backhaul, which obviously has much more higher capacity and can help to alleviate this traffic offload problem. So, you know, from the edge, there's kind of elements of kind of fixed and mobile networks coming together. You know, looking at the IP core, you know, this is kind of carrying you know, all types of traffic today, and this sort of consolidation convergence has already been there for a number of years. If you look at the metro and backhaul, there's a lot of things happening in terms of kind of thinking about how to use packet technologies in parts of mobile networks which used to be circuit switch, TDM, you know, leveraging kind of the same sort of infrastructure that's used today with microwave and fiber, and in the same infrastructure, kind of combine these two things together, and you know, have one set of equipment, one set of technologies that can support all these different types of services, instead of having different sort of networks to support all of them. So essentially, what's happening is a collapsing of layers, and this is kind of a slow process. But kind of what we see is, you know, there's an IP services layer which has to, you know, be there to deliver all the services that we're used to getting. But you know, MPLS, which started off essentially in the IP core, is moving further in, you know, into the metro network, into the aggregation, and even towards the access. So MPLS in some cases can serve kind of a packet multiplexing transport, kind of a packet transport sort of function that spans kind of you know, from you know, from the core all the way potentially to the access, and you know, that's what we can think of kind of as a packet multiplexing or a packet transport layer. We can think of this as now a proper transport network. If we look at kind of the physical media, we have fiber technologies, WDM, microwave. Even if you extend this to the handset, we have radio technology. So this is kind of a generalized, simplified view of the world where we see kind of three functional layers in the network, and the idea obviously is to really consolidate and simplify for, you know, to optimize cost. This is one of the kind of solutions, or one of the techniques in which operators can start to solve kind of the issue of, you know, traffic and mobile networks increasing and improving the cost sort of consideration. I think a key part of this is really looking at, you know, if we have this packet transport MPLS layer which spans over a wide distance in the network, then how can we use, you know, how can we make these different parts of the network talk to each other? We have MPLS, we have MPLS-TP, we have elements of using OTN and DWDM and different technologies. Essentially, because if we're building an end-to-end network, we still need to segment. We still need to scale the network that way. It's important to kind of look at these interconnection points of the two of certain parts of the network that need to be working together. So, you know, what we're calling Unified MPLS is kind of an approach of using MPLS-TP, which is kind of, you know, this technology that has been developed in the IETF over the last. It's in cooperation with the ITU, you know, to develop a packet transport technology, which is kind of on a data plane level, is interoperable and is just label swapping in the same way that MPLS as we know it is today. But it also gives the deterministic sort of characteristics, the bidirectional sort of circuit switch characteristics that we're used to in transport networks. So Unified MPLS is a way that we see of using MPLS-TP to extend this MPLS further into the aggregation and into the access part of the network. This is kind of just a different approach if you compare with another approach that's kind of been proposed in the IETF, which is seamless MPLS. And this is a way to use the kind of IP MPLS, if you like to call it that, which is MPLS as we know it, kind of where we use an IP control plane to to automate topology discovery and routing to build up and signaling to build up our paths. The seamless MPLS case is using this toolkit to extend to extend MPLS to the access. We see a use case in many instances to use MPLS-TP for this function, and that's kind of the idea with Unified MPLS is how to build an end-to-end network using a common packet transport technology, and have it operate in a simple way. So basically, the reason why we're looking at MPLS-TP is because in a lot of mobile networks, the requirements are basically to upgrade what used to be a circuit switch network, but have a packet technology that allows us to have efficiency, of course, of bandwidth and statistical multiplexing. So we can have that, but we can also create these bidirectional paths with co-routed traffic between the two different directions to have fate sharing. We can use the OAM mechanisms that allow us to have fast fault management and performance monitoring for detection of failures and degradations in the network. So I think the important thing here is that this has to kind of plug into the existing IP MPLS network at some point, and that's usually at the edge or the service edge of the network. And this infrastructure there today is already capable of offering IP services, fixed to mobile, pseudo wire handling, IP VPNs, VPLS, all these sort of things. In addition, if we look at end-to-end sort of connectivity, then we have techniques like multi-segment pseudo wire and ways to handle LSP stitching and tunneling that allow us to create LSPs that span end-to-end. And then we can start to look at connections that allow us to give certain services, across different sites. So just to elaborate on this, if we look at the different models here, this is actually this is better with animation. But basically, if we look at the first model with the termination mode, this is kind of a generalization of at a very high level of kind of all fixed and mobile broadband services. We have a backhaul from an access point which goes through the aggregation part of the network into some sort of service edge, and we have sort of a hub PE element that's there to terminate a pseudo wire and hand off to a service node whatever is kind of being aggregated from the access. And this service node in a fixed network is a BRAS. In a mobile network, it's S-Gateway or SGSN, RNC. Once this is handed off, then this is, then it's up to that service node to handle the traffic, either deliver it remotely or interconnected with the internet, with the IX point of the internet. But the connectivity is defined from a backhaul perspective as an access node to the service node. If we look at business VPN connections, which are the next three in this diagram, we're basically connecting an access node to an access node, and these two access nodes can be located in the same metro or the same region, or they can be remote. And in the case that they're remote, they need to be interconnected over a core. And if that core is of a different flavor of the MPLS technology, then we have to think about how to interwork in these sort of scenarios. So the second model here is, or the first model for the AN to AN sort of connectivity is a partitioning model. This is when these two networks talk to each other as peers. So at the LSP level, they are terminating LSPs and doing some sort of stitching between the two. This could even be extended to terminating pseudowires and having stitching between two different pseudowires, so like a multi-segment pseudowire approach, which there's proposals in IETF as to how to do this. An alternative approach is to just layer, to just tunnel whatever packets we have on one side into the core, into a different LSP, and popped out the other side. This can be done in two ways. One is you're interconnecting IP MPLS islands over an MPLS-TP core, or vice versa, MPLS-TP aggregation over an IP MPLS core. In the first case, we've worked with a number of operators that are looking at MPLS-TP in the core, basically as a way to upgrade their TDM backhaul, TDM long haul network. In some variations, they're looking at doing this, automating the routing and traffic engineering signaling using GMPLS. And in some cases, they're looking at using an NMS to basically statically provision a mesh of LSPs in the core. That's one approach. The other approach is if you already have an IP MPLS core and if you want to use that infrastructure and build out sort of new backhaul networks, for example, in mobile networks which are going through a process of being upgraded right now. MPLS-TP can make sense in this case, and in that case we can tunnel MPLS-TP over the IP MPLS core. So basically there's a number of different options here. There's different variants, dependent of course on a number of factors based on the technologies that are already installed and the network conditions. So basically just to look into one case, we're looking a lot at LTE backhaul, and basically we see the opportunity to use MPLS-TP in the aggregation network. Even though LTE is defined, IP is the transport end-to-end, which means that we have IP connections defined by 3GPP, starting from the E node B, going all the way into the evolved packet core, into the EPC, the evolved packet core portion of the network. Even though that's the case, it's still we still see that there's you can still achieve what you need to do having a hub-spoke topology in the aggregation. So basically all your traffic is without doing any processing at the IP level, you can actually just backhaul all your traffic to a hub PE, and then if you need to localize it for X2 traffic, which is there for handover between different E node Bs, we can still meet delay and jitter requirements even if we go back to a centralized site. Another point of this sort of traffic is so far what we've seen is that the actual bandwidth that's required for these sort of connections that are defined in 3GPP for LTE, the amount of bandwidth that's required is not very high. So we're comfortable with this approach, and the good thing about this is that we can use MPLS-TP. We can build a static LSP from a cell site gateway, which is aggregating one or many E node Bs, all the way back to a hub PE. And we can pre-provision backup paths so that the data plane can do whatever sort of protection events that are required. Because there's no control plane involved, we can easily meet sort of 50 millisecond transport failover requirements in that case. So this is kind of the vanilla case of LTE backhaul, where we're just building a transport network in the aggregation. But we think that this network here, because it needs to process IP, we can also have this PE sitting at the hub site, which has to hand over to a serving gateway for in the evolved packet core part of the network. We can integrate the IP processing function. So now, if we do this, we can have this provider edge device, which not only is kind of a termination point for our transport network. We can terminate an LSP and a pseudowire at the transport layer, but we can also process that IP packet and act as kind of the next hop for the E node B. That's kind of one of the things that we see is useful in this approach, and that you need one box instead of two, and you don't need a kind of an external NNI. So this is what. There's obvious benefits to this approach. We think that it's a way to kind of simplify the network even further. And importantly, because this is a full functioning IP edge device, we can start to, we can also reuse it if it makes sense, or if it fits into a current network environment for other services like fixed or fixed services like BRAS, or even video delivery, or even for solutions like Wi-Fi integration. So we see advantages to this sort of approach. So basically, this is kind of a bright picture. I apologize for the marketing slide, but it's basically we see kind of this as a way to bring together two worlds. One is the transport, and the other is kind of the IP side. And we think that there's a lot of different ways of doing this, but essentially we can start to think about kind of ways to collapse the network and build one set of infrastructure for different services, and having different segments of the network talk to each other in a fairly operationally simple sort of way. So that's kind of what we see with this approach. So basically we just to summarize, we see convergence is kind of out of necessity driving operators to look at different ways of cost optimizing the networks. MPLS-TP is an approach that we can use to extend MPLS if you choose to, all the way into the aggregation and access portion of the network. By having this common end-to-end architecture, we can start to think about ways to integrate transport and kind of IP in the carrier network. So that concludes. Thank you.
Thanks. Any questions from the audience? Okay. Thank you. Okay, I have a litany of announcements. So, and then we'll let everyone go to the break a couple minutes early. Tonight, the social, sponsored by Aaron, who is co-hosting here at the hotel. Their program begins tomorrow afternoon. Is on the 33rd floor at the hotel here, basically a pizza party. As well are the elections for NANOG. Polls close at 5 p.m. It's for the steering committee, bylaws, as well as accepting program committee nominations through 5 p.m. today. Coming back from the break at 4:30, we're going to have the DNS track, peering track, and then as well we're going to have IPv6 technology overview part 2, which is a continuation of a tutorial. It's going to cover routing, tunneling, and transition mechanisms. So for those of you kind of in the thick of transition, it's probably a great talk to attend. For those of you that were at the newcomers breakfast, we're going to have a newcomers debrief tomorrow morning. That starts at 8:30 in Washington AB, which is the same room that we were in for the breakfast. That's where you can come tell us, what you got out of this and what you came here for and what we can do better next time. I also like to remind everyone that the NOG lab is open. So I'd like to break now for till 4:30. Thank you very much to our break sponsor, which is NTT America. Thanks.
I've got about 5 presenters lined up to give talks of varying lengths, including myself. And if everything goes according to schedule, we should have some free time after all these talks. So we'd welcome continued discussion on open topics. And Peter from ISC has volunteered to put his asbestos suit back on and stand up here and field some more questions about the politics of China and whatnot. So again, thank you for coming, and I'm going to start off with my friend Matt here is going to give an update on DNSSEC and Common Net. And I'm going to try to find your slides. No, there we go. You probably know how to do this.
More like 10, yeah. Good afternoon, everybody. So as everybody probably knows, there's been a lot going on DNSSEC-wise, and this is just a recap of things that have happened. If you've heard me talk in the past 6 or 9 months, there might not be a whole lot new here, but this will at least bring everybody up to date. So I'm going to talk primarily about the zones that VeriSign had a hand in signing. Here's the timetable. We've had some really significant deployments in the past year or so, starting with the root being signed last summer, closely followed by .edu. We signed .net at the very end of last year, and then the big one was .com on the last day of March this year. So now that .com is signed, if you take a look at the entire domain name market worldwide, and VeriSign has a quarterly publication about the domain name industry called the Domain Name Industry Brief, interestingly enough, and it sizes the entire domain name market worldwide at 200 million names plus or minus, and about 100 million of those plus or minus are in ComNet. So when you look at ComNet and all the other TLDs that are signed, well over half of all domains worldwide can be reached with a chain of trust starting at the root. So that's a much different place that we're in now than we were just a couple of years ago. So at a high level, I thought it would be interesting to talk just what our philosophy was and how we actually went about deploying DNSSEC. We did a slow rollout of the DNSSEC capable name server code at all our resolution sites. So we're running custom code for resolution, our Atlas name server, and we deployed the new code that was DNSSEC capable but without DNSSEC turned on and let that bake a good long time. And then we published this deliberately unvalidatable zone. This is something we came up with in conjunction with ICANN when we were deploying DNSSEC in the root. And the idea is get the effect of sending larger responses with DNSSEC, sending responses with DNSSEC data types in them, but without having people actually depend on the signed zone, and you don't want people actually using it for signing. So what you do is publish a zone that's deliberately broken. It has a key that's not usable. So with that technique in place, then you can do a gradual rollout. That's the big thing, is it lets you do an incremental rollout. Without this, you'd run the risk that you'd publish a legitimately signed zone at one site and no signed zones at any other site. Someone would try to validate it, would work some of the time and not some of the time. So this way it's guaranteed to work none of the time. And so this gradual rollout lets you observe what's happening. Again, this is an exact duplicate of what we did for the root, and it worked very well. Then you relatively quickly unblind, we call it, the unvalidatable zone. In other words, now that you've got this signed zone everywhere, serving up its signed content, which is larger, but not working, then in relatively short order, you start serving the properly signed zone with the exposed legitimate keys. And then the last step is very shortly after that, you add DS records to the root zone. In terms of the provisioning side, this would be what the ICANN accredited registrars see. All the time we have what's called an operational test and evaluation, or an OT&E environment. And this is always a sandbox registry system that the registrars can connect to. This works for new registrars when they want to connect and test their code that they're developing. It also works for existing registrars if they're doing upgrades or changes on their side. They know there's always a place where they can connect that has whatever we're currently have in production on the registration side. So we DNSSEC enabled that long before any of the other work, and that meant that as the registrars were implementing their DNSSEC extensions on the registration side, this is the EPP, the extensible provisioning protocol. That's what the registrars communicate with us to register domain names, that protocol. So that's been DNSSEC enabled, and it was DNSSEC enabled in the sandbox environment for a long time. And the biggest thing, I guess, if I were to summarize here, the final bullet, is that we always allowed a lot of time at each step to just let stuff bake and wait for problems to surface. To just put some dates on this unvalidatable technique as we used it for .com, at the end of February, so about a month before the final deployment, that's when we actually started publishing .com, but with the keys obscured. So we ended up having an entire month where we were serving a signed .com zone that wasn't usable by anybody. And then in late March, the 23rd and the 24th, we actually unblinded the zone. And then we did have this window where theoretically somebody could have noticed the unblinded zone with a legitimate key, configured that key as a trust anchor, and used it. But there's nothing we can do about that. The alternative would be to unblind it and very quickly go into production, and we weren't willing to do that. The whole deployment, well, the root zone deployment, which I don't have on this slide, was remarkably uneventful, no problems. And likewise with .edu, .net, and .com, there was really almost nothing. The one thing we have that's almost not worth mentioning is a bug in a few versions of Bind that affected DNSSEC validation in certain circumstances. So this happened after .net was signed, and it required that name servers be restarted. But we reported that to ISC, and it's since been fixed to the best of my knowledge. So I want to, in all fairness to ISC, we had literally one person report this, so it's barely worth putting on a slide. But I think that speaks well to the whole deployment and the fact of how ready everybody was and how mature DNSSEC is, that it was such a non-event when these big zones were signed. If we look at what happened to the actual traffic after .com was signed, for a long time, about 60% of the queries that come to us, and this is across all DNS queries that we get, about 60% of them request DNSSEC information, and this means they have the DNSSEC OK or the DO bit set. And that figure's been relatively static for years, because for a long time, popular recursive name servers have set this bit. Even if they don't intend to do DNSSEC validation, they still request the DNSSEC metadata in the responses. And when you factor in how much larger the responses get when they are DNSSEC enabled from a signed zone, and the fact that 62% of them are then going to be larger, that adds up to almost exactly a 2x increase in traffic. So basically, we signed .com, and instantly our response size went up 2x. If we look at TCP queries, we expected an increase in TCP queries because we did expect there would be people who would be unable to hear our UDP responses now that they were larger, and that they would then retry over TCP. And this I would qualify as almost none in terms of single digits per second per server beforehand, going into hundreds of queries per second. And when we look at the overall volume of queries, this is nothing. As I say, it's from almost nothing to very few, not anything we were worried about. We also looked at what we called possible TCP failovers. That is, we looked at sources that we heard UDP from, followed by TCP for the same query. And this would indicate potentially somebody having trouble processing our responses. And this was, again, a very, very small increase. This is lost in the noise as well. So this data leads us to believe that we did not strand any large user populations by sending them these larger responses with new record types. We don't think anybody went deaf to our responses. They certainly haven't told us about it. If we look at some numbers about the registration side, as of right now, there are 36 .com.net accredited registrars that have registered at least one signed delegation. In other words, they've sent a DS record for one of their customers. So that's, there are a lot of registrars. There are around 900 registrars, but when you look at the ones that are in associated with one another, there are about 300 families of registrars. So this is roughly 10% of registrars have registered at least one DS record. So, it's not, that's not too shabby, but it's not as much as we'd like to see. There are some exceptions. One registrar has a lot of signed delegations, and a single enterprise has gone ahead and signed lots and lots of its zones, so over 500 of its zones. And then you can see the counts we have. These are real time as of today. Just over 4,000 .com names are signed, and about half that many .net, and just a few in .edu. And thanks to Dwayne, we have scoreboard.verisignlabs.com, so you can always hit that site and see how many signed names there are in ComNet and Edu. And finally, lessons learned. I think the biggest one is that after all the concern there was over signing the root last year, and how methodically and carefully we approached that, followed by how careful VeriSign was with .com and .net and .edu because of the importance of those zones. Because of all that, I think there was a concern in certain quarters, and I think the happiest important news is that the internet didn't break. We saw just just nothing. It was a real non-event. I think we showed that this incremental deployment is possible. Before we did that with the root, I think everybody had assumed that when you deployed DNSSEC for a zone, it had to be a big bang. You had to go from no DNSSEC to all DNSSEC on all of your servers within a very short period of time. And I think the fact that we figured out how to do this incremental deployment with the unvalidatable zone, I think that's a happy discovery. We found this is particularly for the .edu deployment, where we had some very interested and engaged educational institutions that worked with EDUCAUSE and us. We found that the test environment for registrars was very helpful, particularly because we provided a signed version of .edu. So the testers could submit DS records and see them come out at the other end in a test signed version of .edu. Monitoring, as in anything operational, is critical, and there are still minor issues with some of the hardware and software install base. So with that, I'd be happy to take any questions.
Hey, Matt. John Christoph from, is this on? Can you hear? John Christoph from Team Cumry. From the registrars that you listed in a couple slides back, you said there was 35 or some number of them. Can you tell or do you know if there was any particular effort by them to actually go out and do the marketing for DNSSEC and for the one that had the 1,000, was it just that there was one particular registrant who had 1,000 domain names, or what was kind of the success of them doing that, I guess?
Yeah, I'm not the best person at VeriSign to answer those questions because I don't have the direct contact with a lot of the registrars. I know that I can tell you VeriSign has done everything we possibly can to encourage registrars to deploy DNSSEC, just because it's been such a huge effort for us. We don't want it to be in vain. So, for example, we've got a bump-in-the-wire signing service that registrars can use if they want to DNSSEC enable their own signing services. We've written white papers, deployment guides. So we kind of feel like we've done just about everything we can. So I don't know specifically what registrars are doing. I do know that some very, very large registrars are DNSSEC capable, so that's the good news.
Okay, thanks.
All right, thanks.